Hello and welcome to Lab 3, Black Hole Orbit. Today I'm going to find the mass of a black hole and model a star orbiting said black hole using VIDLE and position data from a CSV file. You will see that the mass can be calculated with the help of VPython and our fundamental principles of physics. So let's dive into the physics behind this lab. First is the momentum principle, which states the derivative of momentum with respect to time is equal to the net force. Next, let's look at Newton's universal law of gravitation. It states that the force of gravity between two objects is equal to the product of their masses divided by the distance between them squared, and then multiplied by the gravitational constant, which is approximately 6.67 times 10 to the negative 11th. You'll see how these equations are implemented in my code in the following slides. So first here we set the mass of the star equal to star.m right here. Next, delta t, the change in time, is 86,400 seconds, or 1 day. This line here reads the CSV file, the star data from the CSV file. And then this last while loop here simply calculates the velocity of the star as it travels around the black hole. So this second loop is where the physics gets good. First we define the star's initial and final velocity. Next we calculate the initial and final momentums by multiplying these velocities by the mass of the star here. Using these numbers I can calculate the change in velocity, delta v, and the change in momentum, delta p. Moving forward, dp dt is simply delta p over delta t, or the change in momentum divided by the change in time. And from our momentum principle we know that dp dt equals f net. Now we want to calculate dp dt parallel. First we find the direction of the momentum by dividing p initial by its magnitude. From this we find the change in magnitude of dp dt. The product of p hat and the change in magnitude dp dt, which is set as d mag pdt, gives us dp dt parallel. By definition, this is equal to f net parallel. Now we can find dp dt perpendicular because we know dp dt and dp dt parallel. dp dt perpendicular is given by dp dt minus dp dt parallel. This works because dp dt parallel and dp dt perpendicular added together equal dp dt. Finally, we can calculate the black hole's mass by simply applying Newton's universal law of gravitation. We're solving for mass, and we've calculated for all the other components we need here, and then this last line here calculates for the mass of the black hole. Now we're going to run the code. Here you can see the star orbiting the black hole, and you'll also see the mass of the black hole is printed out here and equal to around 2.58 times 10 to the 31st kilograms. Very large. Now let's address the questions. First, what does it mean? How are f net, f perpendicular, and f parallel different to dp dt and dp dt perpendicular and dp dt parallel? So while these values are equal to each other, that is, f net is equal to dp dt, and f perpendicular and dp dt perpendicular are equal to each other and parallel as well. They're calculated differently. So f net is calculated through Newton's universal law of gravitation in this lab, while the other dp dt's are calculated by looking at changes in velocity. So while they're equal to each other, you get to them in different ways. And now for our second question, what if? So imagine if we had a different black hole and it was placed in the location of our original, and assuming the star motion and everything else remained the same, could we tell the difference between the two? And the answer is no, you could not. You would need at least different star data in your CSV file, or change in another variable to make the calculation. There's no other way to do it. So the answer is no, you cannot. And that's the end of Lab 3, and we thank you very much for watching.